Hi, and welcome to 4.1 Newton's First Law. In this lesson, students will be able to explain Newton's first law and describe inertia. So before we talk about Newton's first law, let's have an overview of where we're going. So we have been in the kinematics subunit of the mechanics unit. Again, kinematics is the study of the motion of an object without considering its mass or external forces. And now is the time for dynamics, which is the study of motion of an object, taking its mass and the forces acting on it into consideration. So we're going to start talking about force, which is awesome. So a typical kinematics question might say a car traveling at 25 meters per second slams on its brakes and skids to a stop in 3 seconds. You know how to calculate how far it travels and what the car's acceleration or deceleration is. A dynamics question might look like this. A 1,500 kilogram car, so that's the mass. Now we're taking mass into account. Traveling at 25 meters per second, slams on its brakes and skids to a stop in 3 seconds. So the same thing that we learned from last time. If it's coming to a stop, the final velocity is 0. So we actually know 4 numbers. We know 1, 2, 3, and then stop, the VF is equal to 0. So again, how far does it go? What's the acceleration? But now we could say, what forces are acting on the car? Can you think of any forces that are acting on this car? We could calculate the weight of the car, and we could calculate the frictional force between the road and the car tires. So we're going to figure out how to do a bunch of different stuff now that we know the mass and how to handle different types of forces. So speaking of forces, you might want to write this down in your notebook. A force is an action exerted on an object which may change the object's state of rest or motion. Force is a vector. A simple way to put it is a force is a push or a pull if you're pushing on something or pulling on something. So imagine pushing on the desk in front of you. You could say, well, I'm pushing this desk with this amount of force. That's the magnitude. How hard are you pushing? How much force? And then in what direction are you pushing? So a force has a direction associated with it as well, which makes it a vector. How do we measure the magnitude? What are the units of force? What would you use? Maybe pounds? Well, pounds is kind of a stupid unit. We better use something different. Would you say grams, kilograms? No, no, no. That's the measure of mass. That's the unit for mass, kilograms and stuff like that. Force is actually measured in newtons. A force is a push or a pull. The SI unit of force is the newton with a capital N. It's very important that you make it a capital N. And at this point, I would normally pass out fig newtons. If you've never had a fig newton before, they're okay. They're pretty good. Some people really like them. Some people, don't like them. But yeah, so that's what I do. But newtons are not named after fig newtons. Like the unit newton is actually named after Sir Isaac Newton, born December 25th, 1642, Christmas Day, and he died on March 20th, 1726. He was an English physicist, mathematician, and natural philosopher. He laid the foundation for classical mechanics. That's what we're studying right now, mechanics. He contributed to the study of optics, which is like how light behaves, and the development of calculus. He formulated the law of universal gravitation, which we'll study in Unit 6, and he formulated the 3 laws of motion that dominated scientists' view of the physical universe for 3 centuries. So we're going to start Unit 4 by talking about Newton's first law and Newton's second law. Then we'll do a little work, and then we'll get into Newton's third law. So there he is, Sir Isaac Newton. What a great guy, that guy. So examples of newtons, like the force. So 1 newton, just so you get an idea, is equal to 100 grams, which is about the weight of an apple. If you're holding an apple, that's like 1 newton of weight. 100 newtons is like 22 pounds, which is like a big bag of ice. So 100 newtons, big bag of ice. 686 newtons or 70 kilograms is a person, a student. That's typically the mass that they'll give for a student in the textbook is about 70 kilograms. That works out to 686 newtons on Earth. And then a car, in case you're wondering how many newtons a car weighs, it's 15,000 newtons or 1,500 kilograms. So those are just some rough estimates so you have an idea of how big a newton is. So again, 1 newton is 1 apple. So that's an idea for how much a newton is. And these are different types of forces. So you can have contact forces, such as applied forces or frictional forces. For these forces, you need to make contact. So in the example I gave before, you're pushing on the desk in front of you. Push on the desk in front of you. You're applying a force to the desk. That's what that means. An applied force. That term applied force comes up again and again. Just think of like pushing on the desk. You're applying a force to the desk. You need to make contact in order to do that. Frictional forces, now rub your hands together. There's friction between your two hands. In Unit 5, we talk about how to calculate the magnitude of that frictional force. But just know that it is a contact force because you need to make contact. Your two hands need to contact each other in order to feel that force. If they're not making contact, then you're just moving your hands back and forth, and there's no frictional force. Non-contact forces or field forces, you don't need to make contact in order to feel this force. So for example, gravity, if you drop your pen or pencil right now, if you hold it up above the floor and you drop it, then gravity is going to exert a force on it. It is exerting a force on it right now without having to make contact with it. Your pen or pencil doesn't need to touch Earth's surface in order for gravity to be felt. It's a non-contact force. Same with electromagnetism. If you've ever played with magnets before, you feel a force between the magnets, whether it be attractive force or a repulsive force. And then same with static electricity. If you ever like slid down a slide before, a plastic slide, and then you feel the force between, maybe you have hairy arms, between the hair on your arms and the slide, there's an attraction there. That's a force that you're feeling. It's a non-contact force. The hair on your arm isn't making contact with the slide after you go down it, but you could still feel that even though your arm isn't in contact with the slide, you could feel a force there. So that's a non-contact force. There's also things known as the strong force and the weak force. Those are also non-contact forces that are field forces, and they're also known as fundamental forces. So let's compare. Which of these four do you think is the strongest? Which of these four do you think is the weakest if you had to rank them? Well, we're going to do that in the next slide. So the strongest force, you might have guessed, is the strong force. And I like this image because they're going to use like a ratio to compare the strength of the different fundamental forces. So what do you think the next strongest non-contact force is? It's actually electromagnetic forces. So if the strong force has a strength of 1, the electromagnetic force has a strength 1/137th as big. And then the weak force is much weaker. Ooh, you probably thought it was gravity. No, gravity's way at the bottom. Look how small gravity is compared to the weak force or even the electromagnetic force. All right, so gravity is actually very relatively weak compared to the other fundamental forces. Why do we feel gravity so much? It's because the Earth is so massive. So we feel that gravitational pull. All right, so now that we have an idea of forces, I will introduce Newton's 3 laws very briefly in this one slide, but then we'll talk more in detail in this lesson about Newton's first law, and then in the subsequent lessons about Newton's second and then third. So just a brief overview. If your net force is equal to 0, the sum of all your forces, they're all canceling each other out, then you're going to be in equilibrium and you're going to have a constant velocity. And Newton's first law states that basically an object at rest will stay at rest, and an object in motion will stay in motion with constant velocity in a straight line unless it's acted upon by a net external force. So if there is a net external force, then you're going to accelerate. You're not going to move with constant velocity. You're going to accelerate, and your net force is equal to the mass times the acceleration. Newton's third law states that every action has an equal and opposite reaction. And here's how I like to remember. So the first law is actually known as the law of inertia. So you could kind of like make this an I for inertia. This is like just a quick way to remember these. Newton's second law, see how it says F is equal to ma? And again, we'll talk about this more in lesson 4.2. But look at this. This is like an F. This is like an M. And then you could kind of make that an A. That one's not that good. And then an action-reaction. Every action has an equal and opposite reaction. So see how this is like symmetrical? The 3 is symmetrical. It's like equal and opposite. So anyway, that's just kind of like a lame way to remember which law is the first, second, and third. Yeah, law of inertia. So please write this down in your notebook. This is Newton's first law. An object at rest remains at rest, and an object in motion continues in motion with constant velocity, that is, constant speed in a straight line. Remember, because velocity is a vector, so you're moving in a straight line. You're not changing your direction. You're not changing your velocity. Your velocity is constant unless the object experiences a net external force. And then if it does experience a net external force, Newton's second law kicks into play. But right now we're saying there's no net force, so the velocity stays constant. And even if that velocity is 0, then it's a constant 0. So it says, in other words, when the net external force on an object is 0, the object's acceleration, or the change in the object's velocity, is equal to 0. So what is net external force? Newton's first law refers to the net force on an object. The net force is the vector sum of all forces acting on an object. The net force on an object can be found by using the methods for finding resultant vectors. So in the example way in the beginning, we were talking about a car, and it said what kind of forces are acting on the car. Well, you have gravity, and then you have this force called the normal force. That's, you know, if it was only gravity, then you would go through the floor, but the floor is exerting an upward force on you so that you don't. And then you could have like a force pushing you forward. Maybe the engine is exerting a force on the wheels, which turn, and then the frictional force resists that motion. You have to take all of these forces into account. You do a vector sum. You add all these vectors together like we normally add vectors, and the vector sum is known as the net force. It says, although several forces are acting on this car, the vector sum of the forces is 0. Thus, the net force is 0, and the car moves at a constant velocity. Okay? So why do they say net force? If you think of like, if you have a lemonade stand, all right, you're selling lemonade, you need to buy lemons and a pitcher and maybe ice and sugar and water. I guess there's costs, right? And then you sell your lemonade for a profit. So your net profit is whatever money the people give you minus the startup cost. That's the net. So it's like net means just adding everything together and finding out what it is. So if this is like the money people gave you, then you have to take away the money that you spent already. So you're adding those together. Yeah, so that's what net force is. So here's an example. Look at that. Wow. An object at rest stays at rest. Look at these leaves. They're at rest, and they tend to stay at rest. Even though the net falls down, it takes them a second to start accelerating due to Earth's gravity, right? So they have oh, I almost gave it away. They have something. What's going on? Why are they staying there? That's weird, right? You would expect them to just go down with the net, but they stay there for a second. What the heck? And then take a look at this. This is some water droplets in space. So look at how they're moving with a constant velocity in a straight line. And the reason that we have to look at them in space is because normally they wouldn't move in a constant velocity in a straight line. On Earth, they would go into projectile motion. Why? Because of Earth's gravity. So there is a net external force on Earth, but in the International Space Station, I'm not going to say that there's no gravity, but they're weightless. So yeah, that's pretty cool. They're moving with constant velocity in a straight line because there's no net external force acting on them. There is going to be a video. This is a video of Chris Hadfield in the International Space Station wringing out a washcloth. He gets a washcloth wet and then he wrings it out. What do you think that would look like? Check out the extension folder, and there's some links in there that'll show you this video in addition to this other video. There's like a better quality video linked there. That's really cool. I'll never get tired of looking at that. But why does this happen? What's causing this? Like what can we say about these things that they behave this way? Why is this happening? It's because they have inertia. Inertia. Yes. Let's learn about inertia. Inertia is the tendency of an object to resist being moved, or if the object is moving, to resist a change in speed or direction. Newton's first law is often referred to as the law of inertia because it states that that in the absence of a net force, a body will preserve its state of motion. Mass is a measure of inertia. So basically, the more mass you have, the more of a tendency you have to remain in your state of motion. Inertia is also thought of as like how lazy an object is or how stubborn it is to change its motion. So for example, if you're sitting on the couch and you're nice and comfortable, you have a lot of inertia because you're not going to want to move from your state of rest. It's going to take a net force to get you to do something and start moving. And the same can be said. So I like to use the example for like studying. If you have a lot of, or even homework, if you have a lot of homework to do, you might not want to start doing it. So if your goal should be to just do one problem. Let's say you have 100 problems to do, and you're sitting on your couch. How are you going to get yourself to start moving? Your goal should be to just do one problem. And then once you open up the textbook, you're on Schoology, you do one problem. Now you're an object in motion, and you might have a tendency to stay in motion. If you have 100 problems to do and you got up and you opened up everything and you did one problem, you're an object in motion. Maybe you'll do the next problem. Maybe you'll do the next problem after that. All right. So instead of saying to yourself, you're sitting on the couch, oh, I have 100 problems to do. Let me go and do 100 problems right now. Or do you say to yourself, I have a lot of work to do, but maybe my goal should just be to do one problem, and then that's a good attainable goal. I'll feel happy if I just do one problem. That's fine, and then I could take a break. But then and then you get yourself to go, and then yeah. So try that out. Like I said, these videos are going to be posted in Schoology. And that's about it. Thanks for watching and have a great day.